point change, and that's good. This is too slow, and too aggressive. Right. And generally, that's how you sort of. And when you're sitting at the panel, that's actually what you do. Yeah, that's too slow. Yeah, okay, that's okay. Right? And the best way to do it is, bro, panel. Okay, guys. Go.
Okay, that's
fine. Right? So you generally, I mean, if the operator is happy, then you go, right? But when you do that, you never have this feeling that, is that the best that you can do, right? Could you have done it better? And so these are sort of what I call heuristics, right? Which is just rule of thumbs. It's like, nah, yeah, sort of okay, right? Feel good sort of factor, right? The other one is using some measure, right? The measurement. So opposite to heuristics, which are sort of rule of thumb, stuff like that. You talk about measurement. How do you measure tuning parameters? And the problem is, to do this, you need either some kind of software. You could use Excel if you have a fast scanning information system like Pi system, right? And there are various software in the market that allows you to do this. And we generally measure it using either one of four, ISE, ITAE, and ITSE. Okay. Most common being IAE, ISE. We from process control fraternity, we haven't instituted it as a requirement, but to a large extent we are trying to push people to do ITA. Right? So this is the integral of absolute error. The integral of absolute error. And it's really simple. I mean, yeah, the names, again, it's built by engineers so that nobody else will understand it. But the idea is actually very, very simple. The concept is very simple. If I wanted to measure, right, that control loop over there, right, how would I do it? Really simple, right? If I just take the error. So I say, hey, between this and that, which one is better? Obviously the second one, right? So if I say this is AA, this is BB, which one is better? You just look at it and you say BB is better. I say, can you prove to me that BB is better? Can you mathematically tell me, and again, we are all KPI driven, right? So you would say, well, BB is 30% better than A. How do we do that, right? So the easiest way to do that is just to calculate error. But the problem with calculating error is, so if I magnify that, so I say, I take this PV1 against a set point, so I measure the error, right? And then I continuously measure the error at each second interval. The problem is that then what happens here? So this is PV, so I do PV minus set point, so this is set point. And I get, this is all positive, but when I come here, it becomes negative, right? And if I add it all together, I sort of cancel each other out. So what do? I take the absolute, right? So then, what does absolute actually mean? Absolute means I'm doing Right. I'm shifting everything to a positive. And then I do the same thing, which is PV minus set point. But now it becomes, the symbol of it is
Absolute.
absolute. Then I sum it up. Simple. Right. What's the alternative for doing that? Instead of taking absolute, I take a square. ISE, integral square error, which then actually makes something like that, right? So that would be the sum of PV minus SP square, and that gives me ISE. Okay? Where I have a sensitive process which is time-based. Now, time-based means that if I have a set point that's like this, and or a process that's like this, or maybe a third one, so I say which one is better, right? Is A better, or B better, or C better? So we would look at it as process control engineers. You would look at it and you say, well, I've got a big overshoot over here, but it got to set point quite fast. Here also got to set point quite fast, but there's a sustained oscillation. I don't like that, right? The operators generally, they want you to get to set point, but they want you to keep the plant stable. Remember, we talked about it, right? I want stability before I want stability after. Dynamic stability is when I transition, I still maintain stability. So I don't want a plant that's stable initially here and then it became unstable. Now, here on the other hand, it takes a bit longer, but then it's more stable. Okay? Now, how do I do a measurement that can tell me all this? Right? That says I'm going to penalize if you are sustained oscillation later on, after your set point change. And so like one way of doing that is to take PV minus set point, right? And I multiply by time. Right? That means if after 10 seconds I still have an oscillation, after 10 seconds I still have an oscillation, the number starts getting bigger. However, if this PV minus set point is near zero, then it doesn't matter. You could have a T of 100, but it's still near zero. Right? On the other hand, if you're still fluctuating, so this term is very big, so this is your error term, and you have your time term. So as long as the error is big, after 100 seconds, you're going to get this term becomes enormously big. So I penalize on fluctuations later on. This is ITAE, integral time, and ITSE is just the same thing over here multiplied. Okay? That's your assessment of performance. And I think we are done with. So I'm not going to talk about algorithm issues. maybe I will do one on the various, one on the different, and then we can stop for break, and we can stop there. Let's see. Okay guys, I need help. Okay, so the last section, 9, is on controllers, right? Controllers.
Belakang tu 5. Belakang tu 5. QAD.
So equation variations, right? Equation variations, we talked about the classic equations. We said equation 1 is change in output is k times error plus k over ti error dt plus k. And we said this is unacceptable, right? Not acceptable. And this is equation 1 in Honeywell and EID in Yoko. This equation doesn't exist in Foxborough because it's not unacceptable, so this option for using this equation in Foxborough doesn't exist. We don't like this equation, and a lot of Petronas plants actually like this equation. Change in output, so another option is k times error plus k over I t error dt plus k dt dpv dt. This is equation 2 in Honeywell and EI-D in Yokogawa. And this is the most common equation used. Okay? Equation 2. This is in Fox, this is SPL lag equal to Dila, you remember? No? She's ex-Fox photo.
X-Fox. One.
I'm not mistaken, it's SPL lag 1. So this is equation used by most common, but you find that there is an error term here and there is an error term here. So when you want to tune this loop, possible, but they're both working on set point. And so what's the issue with this is that both P term and I term works on set point. And you think about it, this doesn't make sense. Why doesn't it make sense? How often does an operator change a set point? Take any process loop, take one process loop, take a temperature loop in a furnace, take whatever loop. How often does an operator change a set point? Never. In a day, maybe once, for a particular loop, right? If he has to continuously change a set point, you have a problem in the process. A plant that is completely stable, operators should not touch anything at all. In fact, for days, he would not need to change a set point for a particular loop. If you have 300 loops in a plant, then he might be changing a little bit here and there, but generally he shouldn't be changing set point. But the focus of this equation is on error, and error is set point minus PV, right? And you think, hey, wait, I've got a problem here. I've got an operator who never changes set point, but I've got an equation who actually emphasizes set point. So can I change that equation? Because what does control loops deal with 99.999% of the day? The disturbances, right? The disturbances in the process. It doesn't deal with set point changes. It deals with disturbances. Disturbances are really small. When you do set point change, how much the operator changes? He changes 1%, he changes 2%, he changes 3%, 5%. What are disturbances? 0.5%, maximum 1%. Small bump here, small bump there. Most of the time processors deal with disturbances, not set points. So how can I build an equation that emphasizes the need to deal with disturbances? Right? That equation is this equation here.